Hey everyone, welcome back to the Summer Pi series, and in this video we'll finally start processing the lensing images that we will be using to train our convolutional neural network. But before we start programming, we'll have to download the data. So to get it, go to the ProjectYumo GitHub, link in the description below, and download the Summer Pi lens dataset. And once you have that, we're ready to start. So we'll begin by importing the necessary libraries. Here we have the image module from the PIL library, which we'll use to manipulate images. We have glob, which allows us to extract the necessary file paths that contain our data. We have random to generate random numbers, which we'll use later. We have matplotlib and numpy, which we've used before. We have torch because we're using PyTorch to do all the deep learning stuff. And then we have Torch Vision, which contains a lot of popular datasets and models that you could use to measure the performance of your own custom model against the previous state of the art. But we won't be using those right now. I want to show you how to organize custom data, since it's a good skill to have when doing any deep learning work. And then we also want to build our own models. And the main module that we're interested in using is the transforms module, which will allow us to transform our images. And then of course we're going to get the Google Colab file so we could upload our dataset to Google Colab. So let's run this, and we'll have the option to choose our data, choose our files. Okay, that was weird. And then pick the dataset that you downloaded from the GitHub. And we'll wait for that to upload to our environment. So once that's downloaded, it should say 100% done. And what we're going to have to do is, because we uploaded a zipped file, so we're going to have to unzip it in the Colab environment. So unzip SummerPi lens dataset.zip. Okay, so now everything's good to go and we could start using it. So in the next code block, what we're going to do is we're gonna just take a look at what the type of data we're working with. We haven't actually seen one of these images that we're working with, so it'd be a good idea to take a look. So let's access the training folder, and then we're gonna access folder A, which are the lensing images. And let's see how they're named. Okay, so they're just numbered, pretty simple. Let's take 33.png. And then to see it, let's say plot.image show sample image. And okay, so this is one of our gravitational lenses. You could see the distortion here. So what we're going to do next is we're going to rotate this image. In deep learning, it's common to augment our images by rotating, scaling, or using other methods, and this helps us artificially increase the size of our dataset. Rotation is good to use on convolutional neural networks because CNNs do not have rotational invariance. This means you could rotate an image and it'll change the way the network predicts. And when you think of how you see a picture of a car, you know it's a car. No matter what orientation it is in, if it's upside down, you know it's a car. But CNNs unfortunately can't do that. Its confidence level changes based on the orientation of the object. So that's something to keep in mind. So we're going to start a new code block where we'll test a rotation. And what we're going to do is say RR for random rotation, transforms.random rotation. And we're just gonna go from 0 to 360. We'll do any random rotation. And then what I'm going to do is TT for toTensor. Remember, we need to convert our data into tensors. And then my transform. So what you could do is, if you have different types of transforms, you could compose them together in a sequence. So what we're going to do is we're going to rotate the image, then convert it to a tensor. Now, I want to see what it looks like rotated, just to get an idea of how this works. So we're gonna say image r equals my transforms. We're applying the transforms on our sample image. And then we're gonna say plot.imshow our rotated image. So let's try that. Invalid. Okay, so we actually, I forgot we need to convert this to a pill image, because you can't ask image show on a tensor, unfortunately. So we'll say convert our rotated image to a pill image. Okay, so you could start to see the rotation. We have these black corners that end up because there's no information there anymore because we rotated it. And now we could start to build the dataset class. So we'll open a new code block. So next what we're going to do is create the dataset class. I'm gonna call it image dataset, and we're gonna inherit the torch.utils.data, the dataset module. And this gives the instructions on how to load data. And we'll be using a data loader constructor, and we'll get into that later though. So let's start with our initiation method, where self root, this is the path or the root directory to our data. Transforms equals none. It's the default value, but we're gonna pass in our transforms that we just made. And then what we're going to do is self.transforms. For this object, we're gonna assign this object's transforms to the ones that we passed in. Next, we're going to extract all the file names for our lensing data, and we'll be using the glob library that we imported earlier. So path a plus slash star dot star. The stars just mean get any file name of any type. So if you put .png, this means get any file with the PNG ending. So, but we could just leave it as that. We're going to do the same thing with our regular galaxy images. So we'll just change this to path B and files A. And then we're done with the initialization method. So next we need to create the getItem method, which instructs how to get an item. So we'll pass in the index and we'll say item A equals self.transforms. I'll explain this in a bit. .open self.files A random dot and int from 0 to length self.files A -1. So what's happening here is that we're going to pick a random number within the range of the length of our data set. So if we have 45 images, we'll pick one random image from there. And then we're going to open that image using the image library or the image module from PIL. And then we're going to transform that image. It's as simple as that. We're going to do the same thing for the regular galaxy images. So just copy and paste and change everything to B. Make sure everything's correct. Okay, cool. And then we're going to return a dictionary that allows us to access the data. So item A, so with a key A, when we pass in A, return to us item A. When we pass in B, return item B. And then we also want the labels. So remember, your loss function requires float values. So we'll need to put 1.0 for lenses, and then B label is 0.0 because there's no lensing occurring, they're just regular galaxies. But we love regular galaxies as well. And then we're going to define a length method, and this basically specifies the size of your data set. Now, usually people will say return length of self.files A. You have 45 lensing images, so that's the size of your data set. But we're going to augment them, right, with the random rotations. So we're going to increase this a little bit, and I'm just going to define it to say 150. That's like 3 times the size of our data. And the reason we could do this is because we're getting random images. We're going to apply random rotation. We get the same lenses but different orientations, and that counts as different data. So we'll just set this to 150. So now we're going to prepare the data using the dataset class that we just made. We'll start off by defining our data path, our root directory, which is pretty much the name of the dataset that we just uploaded. And then we'll say train data loader. And this is where we use the data loader constructor. So torch.utils.data.data loader. And this basically just gives the instruction on how to load in your data and load them in a way that will allow us to train on them. So we'll pass in image dataset, and this gives the instructions on how to get data. So we'll pass in data path, train. We're going to use a train data, of course, and then we'll say transforms equals my transforms that we made earlier. Next, we also have to define the batch size. Remember in one of the previous videos, we went over mini batches and why they're useful and pretty much standard in deep learning. So we're going to set our batch size to 32. This is our mini batch size, the number of images that we'll be training on. And instead of using all our data at once, 150, we're using a small subset of that data, so 32. And we'll say shuffle equals true, because what data loader does is generate the batches of 32 images, and we want to shuffle them so that our model is not training in the same order of batches every single time. And that could help with training, maybe even hurt it, but I would say it's better to shuffle. And we'll do the same thing with the test data. So change this to test. So I don't know if I ran this already. I guess I didn't. Oh, I think this one shouldn't be there. Okay, let's try that. Okay, cool. That works. Make sure if you have a lot of these parentheses and brackets that you check them. And then I think I just ran this and that works. Okay, cool. So now what we're going to do is we're going to get a little better sense of what data loader is doing. So what we're going to do is print out the number of batches. And all you have to do is say length of train data loader. Next, I'm going to extract a sample batch. And to do this, we'll say next iter. We're going to turn our train data loader to be iterable. And we're just going to say get the next batch. And let's say print train data loader. Let's get the A data from that batch. Let's get the B data. And then let's also get the labels. So the image batches should have a very specific size. So let's say data shape. A data shape is the shape of this data loader. And then we'll do pretty much the same thing for B. And for the labels, remember it's just a simple float number, either 1 or 0. So we don't have to worry about that too much. But we're just curious about the data shape size, or the data shape. Number of batches 5, not subscriptable. Oh, sample batch. Sorry about that. So the way you read this is we have 32 images, right? Because we set our batch size to 32, and they have 3 channels, the RGB, and their size 64 by 64. So we have 32 colored images, which is exactly what we wanted. And then we have all the lensing labels. So they're lenses, so of course there'll be 1, and that checks out. Same thing for the regular galaxy images. We extracted 32 of them, and we have their labels as 0. So everything's good. We processed the image, and now we're ready to build our convolutional neural network and start training on these images. And we'll do that in the next video, so I hope to see you there. Peace.